Hello, good morning, everybody, or good afternoon, or good evening, depending on where you're logging in from. Welcome again for this session. I think we are going to continue today's session from yesterday with going a little bit deep into and learning about implementation from zkM. We have Alice here. Alice, I'm not sure if you are going to be joined by Stefan as well, or you're going to take it yourself, but welcome here. Yeah, I would let you make you the co-host real quick, and then you can introduce yourself and then go ahead. So give me one moment, and let me make you the co-host. Okay, Alice, you should be good to go.
Okay, thank you so much, Saif, for the introduction. Yes, today it will just be me for today. If you guys were here yesterday, Stefan from the zkM team, he is lead dev at zkM. He presented more of like an overview of what zkM does. So zkM is building a zk VM called Ziren. I believe he also presented about some of the design considerations in the architecture that him and the dev team chose to make that differentiates us against some other zk VMs in the market right now. And he also talked about use cases. So I'll get to sharing my screen right now. So today is more like a part 2 from yesterday's session that was led by Stefan. So yesterday, he presented how zk VMs work, design considerations, some use cases. But for today's agenda, we'll be first going through the value proposition of using zk VMs. So I think yesterday you guys learned how zk VMs work, but today we'll go over why they're being used. And then also how Ziren, which is zkM's zk VM, works under the hood. And then we'll be, as Saif mentioned, this is more of like a hands-on discussion. So we'll be going over a demo of how you can write your host and guest programs, and from those programs, generate proofs and verify them. And then I'll also show you guys some of the developer tooling that Ziren provides. So just as a recap about what Ziren is, Ziren is the first production-ready open source zk VM that supports the MIPS 32 instruction set architecture. The main use case that we're targeting is verifiable computation. So there's a couple of big use cases that zk VMs target. One is verifiable computation, one is privacy. So we target more of the verifiable computation side, being able to scale computations and then generate and verify proofs from them. We do have privacy capabilities. Within your program, you can choose to keep certain inputs you want private, but that's not our main focus. One of the main use cases that we're building is the entangled rollup architecture protocol. So essentially, you can do cross-chain messaging, like for example, the cross-chain transfer of assets without having to implement traditional bridge architecture. Instead, we use zk-based messaging for the communication. So one of the first use cases that are being built on top of entangled rollup is Goat Network. And then also Ziren offers some comprehensive developer tooling and also a proof network for outsourcing your proof generation. We've recently just opened it up again. So if any of you are building any sort of applications, have a prototype you want to test out, and don't have the local hardware, or say the application you're building, just the local proof generation is not feasible and you need to outsource it somewhere, definitely reach out to us and we'll give you access for the outsourced proof generation with the proving network. So first, in our first part, we'll be briefly going over why zk VMs. So I think you guys are familiar with this proof lifecycle process, but just as an overview, when we are generating a ZK proof, there's a few stages that we have to go through. First is the end user's action. So from your side, you have to determine what is it that I want to be proven. And then you need to decide how will this be executed. So if you're using a ZK VM, this will come in the form of executing your program. And then the next question is, how will this proof be generated? So that's the proof generation aspect. And then you need to see how that proof will be verified. There's both off-chain and on-chain verification for Ziren and for a lot of ZK VMs that currently exist right now. So you can either post your result on a smart contract, deploy it directly on, for example, Ethereum, or you can do off-chain verification. So for example, browser-based verification. This is local verification, but it's a good alternative if you don't really need to do anything on chain. You don't want to incur any gas costs and things like that. And then from there, once you have your generated proof and you verified it, you can determine the resulting actions. So this is where the applications, use cases parts come in. How will this proof be used? So here the main question is, what if a proof of execution can be provided for any type of general computation, not even just those that are blockchain based, but even beyond that? So the role of ZK VMs here is that they kind of handle every single part of this proof lifecycle process, from how this will be proven to how it will be executed, to the proof generation, proof verification parts, and then even how that proof will be used. So every part here in this proof lifecycle is assisted by ZK VMs. So that's the main value proposition here. Basically, ZK VMs provide a really nice developer experience for the end user who wants to use ZK. So ZK VMs like Ziren basically do all of the heavy work when it comes to the execution, the proof generation, the proof verification. So you only need to worry about how you should integrate ZK into your use cases, as opposed to handling under the hood what happens with ZK proof generation and verification. ZK VMs also minimize trust assumptions. So when you're using a standard VM or anything non-ZK related, there are some assumptions that are involved when you're running this computation. You need to assume that the configuration of the VM is correct, the program that encodes the computation is ran correctly, and also the results of that computation that were given to you are correct. So for example, if you are relying on some operator like AWS, you need to trust them and you need to believe that they aren't lying about the results that they give you. So there are a few trust assumptions that you need to use today if you are, say, running some kind of computation on a standard VM. But ZK VMs, what they do is minimize some of these trust assumptions. So instead of trusting the operator, like for example, at AWS or a runtime environment, you instead only need to trust the proof system hardness. So no actor can generate a false proof. You only need to trust the correct implementation of the ZK VM circuit. So I think I might be frozen. We were talking about minimizing trust assumptions. So just as an overview again, these are the trust assumptions that are involved when you are trying to run a computation using a standard VM. But for ZK VMs, instead of trusting the operator or runtime environment, like for example, AWS, you only need to trust the soundness of the proof system. So the idea that no malicious actor can generate a false proof. You need to only trust that the implementation of the ZK VM circuit is correct. So the teams who are designing these ZK VMs correctly implemented the ZK VM circuit. These are highly audited, and they're also open source as well, so you can take a look for yourself. And also the cryptographic assumptions underlying the proof system are correct. So now, compared to the standard VM configuration, now we can replace operational trust with cryptographic trust. And now all you're doing is trusting the math instead of black box runtime where you don't really know what's going on. And the alternative to using a zkVM, traditionally developers have handwritten circuits. So basically you'll have some sort of initial state, you'll have some program written in, for example, CIRCOM. There's some other ZK DSLs or domain-specific languages that are specifically built to use ZK, like, for example, Leonora as well. So all of that is compiled down to a circuit, and then what's output is a final state and a proof accompanying that program that proves that the execution of that program is correct. Here are some comparisons between using a circuit and a zkVM. So zkVMs you can think of as a universal circuit. It's very generalizable. You'll only need to write a zkVM circuit once. So that circuit is made into a VM. Basically, the VM emulates that kind of universal ZK circuit, as opposed to this purely circuit-based approach where you have to basically write a new circuit for every type of program that you want to generate a proof of. So it's a lot more repetitive. And for zkVMs, another big value proposition is that you as a developer can use programs, languages and programming languages that you're already familiar with. So for example, a lot of zkVMs in the market, they are compatible with Rust. For Ziren, we will have compatibility with Go sometime soon, and then C++, for example. So instead of having to learn completely new languages like a ZK DSL, you can instead use languages that you're already familiar with. And another big value proposition is this idea of plug and play. So you as a developer can use the existing infrastructure that's there, use those preferred languages that you're already familiar with, and you don't need to do any of the cryptography or understand like any of the math that is involved with ZK. So you don't need to write custom circuits, you don't need to deal with any complex cryptography, define constraints, all of that. All of those kinds of details, under the hood details of how ZK works, that's abstracted away. So all you need to do is just write your program of the type of computation that you want to generate a proof of. Everything else, all of that process details that goes into proof generation, verification, that's abstracted away from you, and that's handled by the zkVM itself. So zkVMs try to make the developer experience, your guys' experience, as easy as possible. And this is the larger picture of where zkVMs fit in terms of this infra stack and the evolution of how we got there. So as we just talked about, we first started off with handwritten circuits. So developers, you as a developer had to directly handwrite circuits in terms of their constraints. And there's quite a big learning process involved with that. It was very low level, so very similar to, for example, like in the older days when applications were just written in assembly. Now we have much prettier, much higher level languages like Python and Java. But before we had to directly deal with just these lower level languages, and we didn't have those high level representations as of yet. And then came circuit libraries. So now there are some pre-built subcircuits for common cryptographic primitives that developers can use. You no longer have to handwrite every single circuit. You can instead use some pre-built ones. And then came ZK DSLs. So now developers can write in some more familiar programming styles. For example, The Noir language, which was developed by Aztec, they have a Rust-inspired syntax. So it is still a new language you need to learn, but the syntax, if you already developed with Rust, is very similar to that. And then came the idea of generating a generic IR, or intermediate representation. So now compilers can output this generic IR that can compile to different proof systems, and that allows for multi-backend support. So it's more flexible in that way. And then now we have zkVMs. So we can write programs in existing languages without having any circuit knowledge. So zkVMs, as you can see, is the highest abstraction layer so far in this zk infra stack. Now, how does Ziren work? We'll go through this very quickly, but for any of you guys who are interested in how the program execution proof generation process works, this is the high-level process, step by step. You can divide it into 3 different parts. The first part is the program execution. The second part is proof generation, and the third part is proof verification. Within the program execution, you have a program that's written in a higher level language like Rust or Go, which is available with Ziren. And then that program is compiled into an ELF binary. That's the executable format for the MIPS instruction set. And that ELF binary is loaded into the MIPS VM. That MIPS VM will run your compiled program, and the result is an execution trace that represents the entirety of that program, and it's generated for the prover. So first, when you are in that compilation process, once you have your program that's compiled, you'll get a sequence of MIPS, individual MIPS instructions. So for example, in row I, that's just saying add the value of row of register 5 to the value in register 6, store that in register 7. The corresponding table for that is on the right side. So for row I, you can see, well, 13 plus 21 is 34. But the table on the right side is the trace table, your execution trace. So basically, you'll go through all of the zkVM will go through all of these instructions line by line and will output the results in the form of a trace table, which is shown on the right. The prover will use the execution trace to generate a proof that the program was correctly executed. And here are some of the particular steps in that proof generation process. Essentially, first, that trace table that we just saw is divided into smaller segments, and those are just smaller sequential executions from the program execution. Those segments are then divided further into modules, and each instruction or each segment, they're divided into groups of 4 different modules depending on the type of operation that that instruction uses. So for example, all arithmetic related instructions are put into the arithmetic table, all logic-based instructions are put into the logic table, so on. And then from here, we'll go through and generate some Stark proofs. All of those modules are independently proven. So you'll get a proof for each type of table. And then comes the lookup process. So we use this lookup scheme, basically combining those proofs into a single proof for each segment. And then all of those segment proofs are recursively combined into a single continuation proof. And that continuation proof is the proof that represents the correctness of the entire program trace. So this proof is still a Stark-based proof. Stark-based proofs are a little heavier in size. There's both Stark proofs and Snark proofs. Stark proofs are a type of zk proof. You don't need a trusted setup, but they are a bit larger in size. and they're not very ideal for on-chain verification because of their size. So what we do is we do some wrapping. We have a Stark to Snark wrapper, basically the Snark proof. So for example, the Groth16 proof system you guys may have heard of, that's an example of a Snark proof. And those proofs are a lot smaller in size. So it's more ideal for on-chain verification. So from here, we will convert it into an EVM compatible proof, like for example, Groth16. There's another proof format called Plonk, and that enables your final proof to be verified directly on the L1. And then this is external to the zkVM itself, but after generating the proof, you can deploy your verifier logic, the verifying key, onto a contract, so you can verify the result of your proof on-chain. And this is just a high-level overview of all of the details that goes into Ziren and how that relates to each step of that proof lifecycle that we previously discussed about. And this is just an example of using entangled rollups and how that fits into Ziren. So you can, for example, send 100 USDT from your source chain, which in this example is the Ethereum layer 1 to your destination chain. This can be another EVM compatible chain and even non-EVM compatible chains as well, like for example, Avalanche. So you can deposit your 100 USDT onto the corresponding L2. A proof that USDT was burned on that L2 is generated off-chain. That proof is verified on the destination chain, and once verified, that user will receive 100 USDT on the corresponding chain. So here you can do a cross-chain asset transfer without having to rely on a third-party bridge, instead just using cross-chain messaging through ZK proofs. Here are some capabilities, additional optimization techniques and capabilities that Ziren uses. So one is proof aggregation, and basically it can act as a standalone program generating a verifiable proof. That proof can be reused by other programs without having to re-execute the original computation. So over here, essentially, the main value proposition for proof aggregation, if you have a particularly large computation, you can basically split it into smaller segments, generate proofs for each individual segment, and combine them all together in the end. So there's some advantages here in proving efficiency, and a lot of other ZK VMs also use proof aggregation. So essentially just splitting your program and then generating proofs, recursively combining those proofs together to produce a final proof. So proof aggregation is particularly very helpful for very computationally, like a computation with very computationally expensive operations in it. Sometimes breaking things down step by step is much easier to do. zkM and Ziren specifically also offers precompiles as well. So precompiles are used for running specific operations, like for example, a hashing algorithm on special purpose circuits rather on the CPU itself to accelerate performance. So precompiles are like particular circuits that can encode some type of cryptographic operation. And it's analogous to having a specialized chip on your CPU. And its main advantage here is that it can accelerate those kinds of cryptographic operations. Some cryptographic operations are not particularly ZK friendly. So if we were to implement that as an actual circuit, you can have some proving efficiency in terms of the amount of time it takes to generate your proof, and it reduces the overall instruction sequence for your program. So there's a few ways you can use your precompile. You can use it using the zk's SDK or via a system call directly. And those instructions can be constrained inside the zkVM runtime itself. For example, one of the first precompiles that the team implemented was a SHA-2 precompile, basically implementing the block decomposition and hash computation phases of the SHA-256 hash function. And you can reduce proving time and also the number of committed cells before the padding process of the SHA-256 hash algorithm. So you can speed up very specific steps, and from there have some advantages in your proof generation efficiency. Now for the demo itself, what we'll do is we'll utilize zk's project template, which includes a sample host and guest program that proves the values of a generated Fibonacci sequence are correct. We'll go ahead and compile that program, generate a proof for it, deploy a verifier contract, and then post the proof on that contract. This is the general flow of the project template. So remember the 3 phases that we talked about previously that related to the program execution, the proof generation, and proof verification. So essentially what we'll be doing is building our guest program. You can do that in Rust right now. We'll have capabilities in Go later on. And then that guest program will interact with your host program. And then you can either choose local or remote proving. So local proving, you generate that proof using your own local hardware, which is like client-side proving. Remote proving, you could delegate your proof to zk's prover network. So basically outsourcing your proof generation. And that's more beneficial, especially if you have any kind of heavier computations that you want to generate proofs for. And then from there, you can generate a verifier contract. So just going over that first step with program execution, there are 2 types of programs that are used in Ziren. So what we have in our first program is your guest program. That the guest program will encode all the program logic of your computation. And the main capability of the guest program is to execute your compiled ELF that is proven inside the zkVM. The host program sets up the environment for the guest program and evaluates the result from its execution. So in terms of the interactions between the guest and host program, the host will provide inputs to the guest reads those inputs. The guest also writes private outputs to the host will evaluate those private outputs. In addition to that, the guest will also commit to the public outputs, and the host will evaluate those public outputs that are provided by the guest. So that's some intuition behind what the guest and host programs are and how they work together. This is an example of a guest program that's in the project template. So this is specifically generating the Fibonacci numbers so you specify a number n, and then you generate the Fibonacci number corresponding to it. We'll look into some more details of this during the actual demo, but as you can see, this is the main logic for it. So in this main function, we have reading an input from the host, and then this we're just doing the program logic itself. So in this context, computing the n-1th and also nth Fibonacci numbers. And we're just using a standard Rust library function to do that. And then we are wrapping the result and then storing it to be committed for the host. And this is the logic for the host program. So essentially in our main function. We're just decoding those outputs that were provided by the guest. So the nth number, and then the nth minus 1th Fibonacci number, and the number corresponding to the nth Fibonacci number. We are testing to see if those values are indeed correct. And then you can also output the number of cycles that are executed. This is very helpful if you want to see how you can optimize your program. So you can see the number of cycles each instruction takes. And that's just a very helpful way to see which areas of your program you can exactly pinpoint which areas of your program you can further optimize. So the more cycles, the longer the proving time takes. But in seeing which particular parts of your program takes the most cycles, you can then try to optimize it. And then here we're setting up the program for proving, generating the proving and verifying keys. And then here are some options for generating the proof itself. Now for the proof generation, there are two types of proving. As we mentioned before, one is local proving. In the project template itself, this is the feature by default. And that's sometimes, say you're doing some kind of privacy-based application, users are more comfortable with generating proofs on your own hardware. So you're not really exposing any sort of information to anyone else. Everything just stays local. So client-side proving is especially beneficial for any sort of private applications that you want to create. Server-side proving, which involves outsourcing proof generation to high-performance servers, is an alternative for local proving, and it's especially helpful for some computationally intensive tasks. So there's proof networks, for example, zkM currently offers a proof network. There's also proof markets. So these are just being able to serve multiple applications in an open market, and different provers who have the hardware to generate these proofs will basically compete on different prices on different proof generation requests. So instead of having a single application generate these proofs, you can send them to an entire marketplace. And some ZK VMs offer these proof markets as well. So zkM's proving service allows developers to efficiently generate ZKPs. So if you're a developer, you have a prototype ready, and you want to generate proofs, but you don't have the local hardware to do so, you can apply for a spot on our whitelist or directly reach out to us, and we'll give you access to zkM's network prover. For the proof verification aspect, when you verify a proof, you use a certain number of things. So for example, the verifying key, which is generated during the setup phase. You need your public inputs, the proof itself, and then also the result. So for verification, as we previously mentioned, there's two main types. One is on-chain. So you deploy a verifier contract that encodes the verification logic, and that allows for anyone to check a proof against its corresponding public inputs. The good thing about this is that it's verifiable by anyone. The disadvantage is that you need to pay for gas costs. However, gas costs remain constant regardless of the original size of the computation, and that's because of the help of some proof systems like Gross16. So if you have a computation that's a million different steps versus a computation that's just one step, the verification cost and time remain constant. Now for off-chain, this is your alternative to on-chain proving. For Ziren itself, you can run the verification of proofs locally via WASM verification, so browser-based verification, or even in a no STT environment. So that's running in a resource-constrained environment without depending on the Rust standard library. And you can think of it as executing a guest program that is a verifier inside the zkVM. So this is really great for almost like recursive proving. Now for verifying your proofs on-chain, use the verifier key. That verifier logic is encoded in the smart contract, makes verification public and immutable. And your deployed verifier contract with your posted proof will determine if your proof is valid or invalid. Now for the walkthrough demo, this is the project template that we'll be using. So if you guys want to do this in your own time later on, feel free to clone this repository. I'll also put the link in the chat. Give me one moment. So if you guys want to do this on your end, this is the link to the project template. And going back to sharing my screen, we have a quick start example that goes through the end-to-end process of using the project template linked in our docs, so you can follow that as well. What I mentioned before about cycle tracking, we have an example where you can help measure the execution cost of your guest programs. And this example over here consists of a host and 2 guest programs that can help output how many cycles you're using in your program. So it's very good to see which parts of your program you want to be optimized if it's taking a large amount of cycles. Here's some installation requirements in terms of Rust, and then also if you want to use the Foundry toolchain to generate some Foundry contracts for the deployment of your verified contracts, you need to install that as well. And if you guys are doing this on your own end later on and you need some assistance or running into some installation issues, just feel free to message me. I'll give you my contact information in the end. So right now I will transfer to sharing the project template itself. Okay, let me just, okay. So this is the project template. In terms of what it contains, there is a guest directory containing your guest program. There is a host directory containing your host program, and then also a contracts directory. So it contains some sample contracts for the example of proving the Fibonacci sequence, and then also some tests there as well. So it's helpful if you want some, it's especially helpful to just execute your program and use those tests before deploying it on chain where you have to pay for gas costs. But essentially what we have over here, if you go to your guest, to the main guest program, we can see this is the logic of the guest program implementation that we saw previously. Going to our host program, the main program over there, this is the all of the code of the host program, which we also saw just then. So now going into the actual steps, all of the steps are the README as well as in the quick start. What we'll do first is generate our proof. So what we can first go into is our host program. And then there's a couple of different proofs that we provide. So one is a core proof, another is the compressed proof, and then EVM compatible proofs, which includes Groth 16 and Planck proofs. So to generate your core proof, you'll run cargo run release core, And keep in mind that you'll also need to install your toolchain as well. There's a section in docs which goes through how you can install the zkM toolchain, so you can just have these very nice command line interface commands for your proof generation. So because this was a Stark-based proof, it was pretty fast, and also the computation itself is fast as well. We were generating the 20th and also 19th Fibonacci number, and we can see that we successfully generated the proof. If you want to do on-chain verification, you need to use either the Groth16 or Planck proofs. So Groth16 proofs are more preferable. The command for that is cargo run release in EVM, and then you specify your proof system to be Groth16 over here. So I'll make this a little bigger so you guys can see. And this will take a bit longer than the Stark proof itself. So for the sake of time, I'm not going to run or generate a new Groth16 proof. But as when you do this on your own end, it will store the proof itself in the fixture under contracts. So this is a Groth16 proof that I previously generated. Over here, this is the proof itself. Here were the public values, the verification key that was generated during setup, and then also the public values. So our public values are the nth Fibonacci number that we wanted to generate, which in this case was 20, and then the Fibonacci numbers corresponding to the 20th and 19th Fibonacci number. So that's what your fixture looks like. And this is one of the Groth16 fixtures that I previously generated prior to this demo. And then from here, once we've generated our proof, we can go on to the proof verification part. So in your .env file, you can specify, so by default, it's local proving. If you wanted to do network proving, you would specify network instead of local instead. And we have some instructions in this link to our docs over here in terms of the configuration for the network if you wanted to do server-side proving. But for now, just for this demo, we'll do local proving. And again, if you guys are doing this on your own end and you have access to zkM's prover network, you need assistance with setting it up, feel free to message me and I can help with that. So going back over here, I wanted to mention that you have the option to retrieve your verification key if you need it during the deployment of your contract. However, it is stored in your fixtures, but in case you wanted to see it, you can run the command cargo run release bin and then v key, and then it'll run and output the verification key itself. And that verification key is tied specifically to the program that you're generating a proof of. So it's specific to the program itself. So you can't use one verification key for another type of use case or another type of program that you want to generate a proof of. And that makes it so that when you're verifying a proof, if it's a false proof, you won't be able to verify it. It'll revert. So this makes it so that the proof itself, you know that the proof itself is tied to a specific program. And then for the verification part itself, exiting out of this directory, we'll go into the contracts. And then since we're using Foundry for this, we can first run some of the tests that are contained in our template, and it says passed for all of them. So now we know we're ready to deploy this on our main verifier contract. And then here is the command I'm highlighting right now of broadcasting it to a test network. So right now you can, for example, broadcast your verifier contract on Sepolia. So some of the arguments you need to specify here. This is for the GROT16 proof, your RPC URL, and then for this private key part, just as a suggestion, because we're just deploying it on a private network, just use a wallet where you just have your testnet tokens on it, just to be safe. So running this, we'll see over here that our script, which encodes the proving logic of the GROT16 proving system, was run successfully. And then you can see the success hash over here. So going to Sepolia itself, let me just maximize this. Sepolia Etherscan. We can paste the contract address that was outputted and see that we were able to successfully create and deploy a verifier contract. So that is how you can use the project template demo to first generate your proof from the host and guest programs, and then verify your proof and deploy it to some kind of smart contract on, for example, Sepolia, which is a test network. And just to note, going back to our presentation here, let me resume sharing. Just to note, the developer teams are also in the near future going to plan out a suite of verifier contracts, so you'll be able to deploy your proofs on mainnet, and then also on other types of EVM compatible networks, not just on EVM itself. So be sure to look out for that announcement. Going back over here, I do want to quickly mention, in our demo, we went through the process of doing on-chain verification when we deployed our verifier contract. We also have a repo that's available, and the link is over here. This is for using the WASM verifier. So you can generate WASM bindings, basically being able to allow for a web-based environment to interact with your proving and verification logic that's written in Rust. You can compile and package your Rust code into a WASM module, and this makes it possible for browser-based verification. The proof generation aspect is compatible with the different proving types that we offer, including the Stark, GROT16, and Plonk proofs. But unlike on-chain verification, where you can only use GROT16 or Plonk proofs, you can also, with the WASM verifier, directly verify them using the Stark proofs. So over here, there's a little less overhead, because if you wanted to generate Stark proofs and then verify them, you don't have to go through that Stark to Snark wrapping process that we previously mentioned. So there's a little less overhead. And then you can directly do your browser proof verification. So that's a little note that I wanted to mention. You can try out your off-chain proof verification by cloning this repo over here. And here's some more information about our socials. I'll also put my contact information in the chat below. So if you guys are interested in doing this on your own, or if you want some more information, and if you need some help throughout the process, just feel free to message me. Oh, I see we have a question.
Yeah, okay, Alice, GM. So basically, what I wanted to ask was, I actually wasn't here from the outset. So what I want to ask is zkM, right? Is it just for EVM contracts, or it can be used like cross-chain? That's just my question.
Oh, yes. So are you referring to the proof verification itself?
Yeah. The proof verification itself.
Yeah, proof verification itself, we're only right now compatible with EVM compatible networks. So right now we're still in the testnet phase with it. So you can only deploy your proofs on a test network. Um, so right now it's it's just EVM compatible. Yeah, thank you for your question. Does anyone else have any questions? I just put my email in the chat and then also put my Telegram. Yes.
Okay. You mentioned about the program, writing program, guest program. You say that it executes the compile elf, ELF. I want to know the full meaning of it. Like, what does it mean?
So ELF is an executable linkable format. Basically, it is a compiled version of your higher level program that you wrote by yourself. And it's a specific format that makes it readable for the VM itself.
All right, thank you.
Yeah, thank you so much. And yeah, this is not just for Ziren or zkM. All zk VMs need to do this because the VM itself is not able to directly read the code that you write. That has to be fed into a compiler to generate that compiled program that's readable for the VM. So this is universal throughout all zk VMs. Does anyone else have any questions? And again, if you guys wanted to try this out on your own end, or if you have any questions later on, I just put my contact information in the chat. So I put my email and also my Telegram. Feel free to message me.
Yes.
But other than that, yeah, thank you so much, everyone, for joining. And thank you, Saif, for inviting the zkM team to present.
Yes, of course. No, I think you guys are doing some good work out there, and I want to thank everybody to come here. I mean, feel free to explore, test, play around with the code, keep learning and building. I do want to mention that this video will be out on the zkMonk channel as well, so you can go back and visit some portion of that. Obviously, for further question, you can contact. There is contact information there, and you should also be able to do that on the Discord channel. But yeah, you reach out to zkM channel. Feel free to do that, or you can reach out to zkMonk, and they're there to support as well. Finally, thank you, Ellis, for your time, and everybody for joining here on a Sunday morning.
Thank you so much, everyone.
Bye.
Yeah. Bye, everyone. Hope you enjoy the rest of your weekend. All right, bye.
You too. Bye.